Welcome to Understand the Math. In this video, we're going to learn about sequences. We'll start by talking about what an infinite sequence is, and then walk through some examples where we'll find the terms in a sequence. After that, we'll go over how to find the nth term of a sequence, and then wrap up by learning about partial sums and walk through an example of how to find the nth partial sum of a sequence. We're going to start by learning about an infinite sequence and its terms. An infinite sequence is just an ordered list of numbers that continues without end. Let me show you some examples. The sequence 2, 4, 6, 8 is called the sequence of even natural numbers. The sequence 1, 3, 5, 7 is called the sequence of odd natural numbers. And then the sequence 1, 1, 2, 3, 5, 8, 13, and numbers after that is called the Fibonacci sequence. This is one of the most famous sequences in mathematics and appears in nature, art, computer science, and even in finance. Each number in a sequence is called a term, and the terms in a sequence can be written as A1, which is the first term, A2, the second term, and then all the way down to A sub n, which is the nth term. Many times a sequence starts with the term A sub 1, but sometimes a sequence will start with the term A0 instead of A1. Often, we want to find all the terms in a sequence. We can do this by finding a formula for the nth term or defining the sequence recursively, and I'll show you exactly what this looks like. The nth term of the sequence of even natural numbers can be written as A sub n is equal to 2 times n, and then the nth term of the sequence of odd natural numbers can be written as A sub n is equal to 2n minus 1. If you go on to study calculus, you're going to use terms just like this. The last sequence that I've listed is one that is defined recursively. This is the Fibonacci sequence, and it's defined recursively by A sub n is equal to A sub n minus 1 plus A sub n minus 2, where A sub 1 is 1 and A sub 2 is 1. This formula right here just means that the next term is the term before it plus the term before that. Let's see how this works. If we have 8, it's equal to 3 plus 5. Let's now look at some examples where we're going to find the first 4 terms of a given sequence. In our first example, we're told that A sub n, the nth term, is equal to 3n minus 2. We're going to use that to find the first 4 terms in the sequence. Our first term is A sub 1, and all we're going to do is go up into our formula and substitute 1 for n. So this is 3 times 1 minus 2 is equal to 1. Our second term is A sub 2, so this is just 3 times 2 minus 2. So this is 6 minus 2, which is equal to 4. We'll do the same thing for A sub 3. This is 3 times 3 minus 2. This is 9 minus 2, which is 7. And then our fourth term, A sub 4, is 3 times 4 minus 2, which gives us 12 minus 2, which is 10. So the first 4 terms in our sequence are 1, 4, 7, and 10. Let's now look at our second example. This one is a little bit more complicated because it has a minus 1 to the n in it. We'll start just like we did before. We're going to calculate A1. So wherever we have an n, we're going to plug in 1. So this is minus 1 to the 1, all divided by 1 squared, which is just minus 1. Now let's let n be equal to 2. So this is minus 1 squared, all divided by 2 squared. So this is 1 divided by 4. Then A3 is just minus 1 cubed, all divided by 3 squared. Minus 1 cubed is minus 1, so we have a minus 1 over 9. And then lastly, A sub 4 is minus 1 to the 4th, all divided by 4 squared. So this is equal to 1 over 16. Our terms then are minus 1, 1/4, minus 1/9, and 1 over 16. Notice that when you have a minus 1 to the n, the sign alternates, and it starts with a minus. Let's now look at our third example. This is an example where our series is defined recursively. A1 is given to us, and it's equal to 1. Now let's find A2. Using our formula right here, our A2 is equal to 2 times the term before it, which is A1 plus 1. So this is just 2 times 1 plus 1, which is equal to 3. Now let's find A3. A3 is going to be 2 times the term before it, so that's A2 plus 1. So this is 2 times A2, which we just found to be 3, plus 1 is equal to 7. And then I would suggest you pause the video and see if you can do this next one on your own. I bet you can. A to the 4th is then 2 times the term before it, so that's A3 plus 1. So this is 2 times A3, which we just found to be 7, plus 1, gives us 14 plus 1, which is 15. So the terms in our sequence are 1, 3, 7, and 15. Let's now learn how to find the nth term of a sequence. Finding the nth term of a sequence is really useful because it gives us a formula to find any term in that sequence. Because this is a little bit more complicated, I've written down 2 steps that we can follow just to make things easier. When we find the nth term of a sequence, the first step is to set the first few terms equal to A1, A2, A3, A4, etc. And then the second step is to look for patterns. We're going to look for squares, cubes, or alternating signs to find A sub n. Here's our examples. Our first sequence is the numbers 1, 4, 9, 16, and we want to find the nth term of the sequence. Let's start by writing down our first few terms. Our first term is A1, and it's equal to 1. Our second term is A2, and it's equal to 4. Our third term, A3, is equal to 9. And then our fourth term, A4, is equal to 16. I'm going to start by looking at A2 only because A1 is equal to 1, and it's really hard to find a pattern with that. What we want to do is come up with a formula for A sub n. So we need to look at the subscript of our term and see how to write that term in terms of that subscript. For A2, we can write 4 as 2 squared. Now let's look at A3. We can write 9 as 3 squared. And then A4, we can write that as 4 squared. So our term is just going to be that subscript number squared. Over here on the right, that gives us A sub n is just equal to n squared. Let's now look at our second one. This one has fractions in it. Just like we did for the first one, we are going to start by writing down the terms. A1 is equal to 1/2. A2 is equal to 3/4. A3 is equal to 5/6. And then A4 is equal to 7/8. Let's see if we can find a pattern. Notice that the numerators in our terms are 1, 3, 5, and 7. Those are odd numbers, so I'm going to write down that the numerators are odd numbers. Now let's look at the denominators. They are 2, 4, 6, and 8. So those are even numbers. So let's write down that the denominators are even numbers. We found on the previous page that even numbers can be represented by 2n and odd numbers can be represented by 2n minus 1. It may not be a bad idea to memorize that. Using this, we can then write down that a sub n is going to be our numerator, which will be 2n minus 1, divided by the denominator, which is 2n. Let's now look at our third example. I wanted to show you a sequence that has negative and positive numbers in it. Just like we did before, we're going to start out by writing down our terms. A1 is equal to minus 3. A2 is equal to 9. A3 is equal to minus 27. And then A4 is equal to 81. Let's not worry about the plus and the minus for right now, and let's instead see if we can see a pattern in the numbers. Our numbers are 3, 9, 27, and 81. Those are actually powers of 3. So let's write these numbers as powers of 3. We can think of minus 3 as minus 3 to the 1. We can think of 9 as 3 squared. We can think of minus 27 as minus 3 cubed, and then we can think of 81 as 3 to the 4th. Let's now compare our powers in our numbers to our subscript. A1 is 3 to the 1, A2 is 3 squared, A3 is 3 cubed, and then A4 is 3 to the 4th. Now let's think about our negatives and our positives. Our terms alternate between negative and positive, and they start with a negative. On the lower right here, I've written down a formula that we can use, and this is standard for sequences that have positive and negative numbers in them. If we start with a negative 1, we can write that as minus 1 raised to the n. If our series starts with a positive 1 and then goes to a negative, we can write it as minus 1 to the n plus 1. Now I think we have enough that we can write down a sub n. A sub n is going to be minus 1 to the n times 3 to the n. That wasn't so bad. I know these nth terms seem hard right now, but with some practice, you can definitely get good at doing these. Let's now look at partial sums and an example. The partial sum of a sequence is the sum of a finite number of terms from that sequence, starting from the first term up to a specific term. We're going to assume that our sequence is A1, A2, all the way up to AN, and then beyond that. Here's what our partial sums look like. S sub 1 is our first partial sum, and it's just A1. S sub 2 is our second partial sum, and it's A1 plus A2. And then S sub 3 is our third partial sum, and it's just A1, A2, A3. And then you can see the pattern here. S sub n is called our nth partial sum, and it just adds all the terms starting with A1 going up to A sub n. Let's now look at an example where we are going to find the first 4 partial sums and then the nth partial sum of the sequence. We are given the nth term of the sequence, and it's equal to 2 divided by 3 raised to the nth power. Let's start with our first partial sum, that's s sub 1, and it's just equal to a1. So we're going to look up at our formula, and we're going to plug in that n is equal to 1. So we're going to get 2 divided by 3. I'm going to write my fractions like that just to save space. Now let's look at our second partial sum, s sub 2. This is just a1 plus a2. We just found a1, and that's 2/3. And then we're going to add to that a2. For a2, we're going to look up at our formula, plug in n is equal to 2. So this is 2 over 3 squared. This gives us 2/3 plus 2/9. We'll write our 2/3 in terms of ninths. So we're going to multiply the top and the bottom by 3. So this gives us 6 over 9 plus 2 over 9, and that's equal to 8 over 9. Now let's find S3, our third partial sum. This is going to be A1 plus A2 plus A3. We already found A1 plus A2, so we don't need to compute that again. So let's just start by writing down what that is. We found that to be 8 over 9. And now we're going to add A3. We're going to go up to our formula and set n equal to 3. So this is 2 divided by 3 cubed. So this is 8 over 9 plus 2 over 27. Let's write our 8 over 9 in terms of a number over 27. So we're going to multiply the top and bottom by 3. This gives us 24 over 27 plus 2 over 27, and that's equal to 26 over 27. Now that we have a lot of numbers floating around here, I'm going to go ahead and let's highlight our answers. We had 2/3 and then 8/9, and now we have 26 over 27. Let's now find S sub 4. This is A1 plus A2 plus A3 plus A4. A1 plus A2 plus A3 is S3, and that was 26 over 27. And now we're going to add A4, go back up to the formula, plug in n as 4, and we get 2 over 3 to the 4th. So this is 26 over 27 plus 2 over 3 to the 4th, which is 81. Let's come down here. We're going to write 26 over 27 in terms of a number divided by 81. So we'll multiply the top and bottom by 3. So we're going to get 26 times 3 all over 81 plus 2 over 81. I wrote that down because that's just a little bit too much to keep in our head. 26 times 3 is 60 plus 18, so that's 78. So we have 78 plus 2 all over 81 gives us an 80 over 81. And let's highlight that. Now what we have to do is find a pattern and find S sub n. When I look at the numbers that we have highlighted in green, I see a pattern for the denominators. That's 3, 9, 27, 81. Can you see that those numbers are powers of 3? The denominator of S1 is 3 to the 1. The denominator of S2 is 3 squared. The denominator of S3 is 3 cubed, and you see the pattern. So let's write down that our denominator is going to be 3 to the n. Now let's look at the numerator. Can you see that the numerator in each of our numbers is 1 less than the denominator? So we can write the numerator as 3 to the n minus 1. And now we have our formula for our nth partial sum. And that's it. You now know what sequences are, how to find specific terms in the nth term, and how to find partial sums. If this video has been helpful to you, please consider subscribing to my channel.
Keep believing in yourself and have a great rest of your day.